Unit 4, Lesson 4. We're evaluating the definite integral using geometry. So the deal is the integral, the definite integral from A to B, remember you read from the bottom to the top on the integral, of a function f of x with respect to x, is the exact area. This should say area, not r. This is the exact area under the function f of x on the interval from a to b. So sometimes when you graph a function, you're going to create a rectangle, a trapezoid, a triangle, a semicircle. You already know the area formula for these circles. So why overcomplicate it with a rectangular approximation method if you're just looking at one big rectangle or you're looking at a semicircle? If the function creates a shape that you know, just find the area. That's the point of doing an integral. So, for example, it says rectangle. So I know you know, but I'm just going to sneak. Area equals base times height for a rectangle. Triangles are 1/2 base times height. Circles are pi r squared. Trapezoids are probably the one that most people tend to forget. These are the height over 2, base 1 plus base 2. And then squares, it is just base times height, but you could also say side squared for a square. So these are all area formulas from geometry that we know. So if you're asked to evaluate a definite integral, step 1 here, sketch the function. 2, figure out what shape it is and say, hey, I know the area formula for that. And then evaluate the area using geometry. Even though it's an integral, we just need area, so you can use your geometry formula. Let's take a look at the first one. We've got the function f of x equals the constant 5 on the interval from 0 to 3. So I get that by looking at the integral. The integral from 0 to 3, whatever is in between the integral symbol and the dx, that's our function. So if we sketch this, let's draw in an x and y axis. And we've got up 1, 2, 3, 4, 5. And that's just a horizontal line, f of x equals 5. And if we block off the interval from 0 to 3, the dx part of this lets us know that that's what we're stopping at the x-axis. With respect to x, the x-axis is always a bottom boundary from the function to the x-axis. And we look at this and say, hey, it's just a big rectangle. And we can count the boxes for the base is 3 and the height is 5. So our integral is base times height. The integral from 0 to 3 of 5 dx, I'm just going to rewrite it, is 5 times 3, or 15. Easy peasy. Now, number 3, since I screenshotted this, we're just going to go number 3 since it's to the right of this. This is a function that maybe at first you might feel like, oh, I wouldn't know what that looks like. But once we go over it, you're going to be comfortable recognizing this. The square root of, and let's just write it over here, f of x equals the square root of r squared minus x squared is a semicircle. It's just the full circle from geometry was x squared plus y squared equals r squared. And this is solved for y. And since it's a function, it's just the top half. The radius doesn't always have to be a perfect square, but if it's a non-calculator question, it usually is. So since this r squared is 9, then r is just 3. So we're looking at a semicircle with a radius of 3. Just the top half because it's a function. So 3 to the right, 3 up, 3 to the left.
I feel like I should know this, but I don't. It's negative, so I thought it was downward, but that's not right. Like a negative.
No, because what happens is, and this will help you, the general equation for a circle is x squared plus y squared equals r squared. That's centered at the origin.
Also minus the x.
Exactly,
Okay.
exactly.
Thank you.
So it's not like a parabola.
Gotcha. Thank you.
Then the other thing that we have to pay attention to this is the interval. Yes, the function is a semicircle, but look at your interval here. It's from 0 to 3. So it's only really asking us for a quarter of the circle. So we know the area formula for a full circle. Area for a full circle is pi r squared. So then if we have a quarter circle, we're just going to do pi r squared divided by 4. Or if you wanted to say times 1/4, either way. So since our radius is the 3, the area for this one is going to be pi times 3 squared divided by 4, or a final answer of 9 pi over 4. So after you sketch it, you have to pay attention to the interval. If it was from -3 to +3, then you'd be dividing by 2. It'd only be half a circle. This time it was a quarter of a circle. Let's take a look at the next one. All right, this one, my function is in the form of y equals mx plus b. This is a linear function. So from 0 to 2, I'm noticing that my y-intercept is 5, so I'm going to put my x-axis low since I only have a little piece of the graph. So starting at 5, we then go up 2 over 1, up 2 over 1, and then I kind of fall off the graph here. Once you sketch your function, you're then going to block off the interval from 0 to 2. So from 0 to 2, if we shade this in, this is a trapezoid. A trapezoid has 2 parallel sides, and those are the vertical lines. That's your base 1, base 2. So the first one is 5 boxes. The next one goes up 6, 7, 8, 9 boxes. So the area formula is half the height. Well, this time, the height of a shape is always the perpendicular distance between those 2 bases. So our height is the 2. So 2 over 2, 5 plus 9. 2 over 2 is just 1. 9 plus 5, 14. Now, I'm really pushing the trapezoid formula because tomorrow we're going to learn trapezoidal rule. So we can't avoid trapezoid formula. And it's not one that's necessarily just at the tip of your tongue. So the more you hear it, the easier it will just be to refresh your memory with it. With that said, we just have to get area. For this question, I did not have to do trapezoid rule. If I wanted to split this up, and say, I see a rectangle and then a triangle, do them separately, add them together, you're going to get the same answer. Totally fine. So it's either one big trapezoid or it's a combination of a rectangle and a triangle. It doesn't matter how you do it. So if we did a rectangle, that has a base of 2 and a height of 5, plus then the triangle is 1/2, the base times, and then the height of this is just 1, 2, 3, 4. That splits it into 4 and 5. So then I have 10 plus 4, and I get 14 either way. The ultimate goal is to figure out the area, so however you get there is fine. Questions? Another function that you kind of have to know how to sketch without the use of a calculator is absolute value. And that's your v function, where the turning point is at 0, 0. But if we look at this function on number 4, we're subtracting the absolute value. So this time it is going to be, what did I just do? There we go. It is going to be negative. So this is going to be reflected, the negative. And then the 1 in the front, when you add 1, it's going to be a vertical shift. So if I take my V for absolute value, turn it upside down, and shift it up 1 box, I'm going to have that corner up here at 1. What I love about this one is I feel like it's going to pull together the understanding of what that dx is. Dx means with respect to x. So when you're trying to create the shape, you're always going to utilize the x-axis as the bottom boundary. So it is this little triangle here. You could do 2 triangles or you could do 1 big triangle. The base is 2 boxes. And the height always has to be that perpendicular distance, so it's just a 1. So we'd have 1/2, 2 times 1. So we'd have an integral, which is the area, as 1. Questions?
I have a question.
Yeah.
On number 2, I missed it, but like 2 over 2, why is it 2 over 2?
Because the area formula for a trapezoid is height over 2, base 1 plus base 2. So the height was 2, and it's always divided by 2, just like a triangle is divided by 2.
Wait, where was the height 2?
Down here.
Oh, okay.
The height of a trapezoid is the perpendicular distance between the parallel bases.
Okay, got it.
Good. Other questions? All right, let's take a look at number 5. It wants me to evaluate the integral from 0 to 10. So that's all the space under here. Now, I kind of stole this from another question. On the AP or on the test, you would have to have a little bit of a setup that this function f of x was created by a quarter of a circle and a line, so that you would know for sure that that was a piece of a circle in order to use geometry. I'm just going to tell you that now, but on a test, it would be clear that that was a piece of a circle. This is now just not one shape that I know, but like I said before, you just have to get the area. So if I split this up like a little puzzle, I've got a big rectangle down here. Then I've got a quarter of a circle up here. And then I have a triangle here. So if I need the full area to the x-axis, I can just break it up into the different shapes. So let's first do our rectangle. The area of the rectangle is the full base of 10, and then the height of just 2 boxes. So 10 times 2 is 20. Then let's do this is a quarter of a circle. So pi times my radius goes up to 5, right? The radius is b from here, the center, out. And then divided by 4 for a quarter of a circle. So 25 pi over 4. And then last I have the area of that triangle. The base is 5, the height is 3. So 1/2, 5 times 3. 5 times 3 is 15. Half of that is, let's say, 7.5. So my integral that they're asking me to solve is going to be the sum of all of it. So 20 plus 7.5 plus the 25 pi over 4. So we can call this 27.5 plus 25 pi over 4. And without a calculator, we'd have to leave it in terms of pi. Questions? All right. Let's flip over. Just like with derivatives, integrals are going to be put into some of our application problems. And one of the things is physics. An integral is the opposite of the derivative. So when we're dealing with physics applications, the original function is the position, first derivative is velocity, second derivative is acceleration. As we learn more about integrals, it's kind of bringing us backwards. When we find the area under the curve, if that curve happens to be a velocity graph, the area under the curve is actually the displacement. The reason why this happens is in an integral, we actually have negative area. Negative area is any area that falls below the x-axis. So when we're dealing with an integral, we have signed area. The signed area of the region is the area such that area of the graph on or above the x-axis is positive. So like in this graph here, this semicircle is positive, this triangle is positive, but area below the x-axis is going to be negative. So this triangle, notice that I'm always using the x-axis as a boundary to help me draw the shapes. All of the area goes to the x-axis. That's the dx part of the integral. Below the x-axis is negative. And I always like to just talk a little bit about the physics here because it just gives it a context. It's a direction that you're going backwards a distance traveled. So signed area correlates with displacement. So I'm just going to write over here the integral from a to b if we did of velocity, v of t dt. That's what I'm really referring to as displacement if this was a velocity. So when you're asked to do an integral from a to b of f of x dx, it's really asking you for the net area on that interval. Basically, you're going to take the area above the x-axis and then subtract area below the x-axis. I want you to keep it with that, area above minus area below. When you are calculating the areas for each individual shape, do it in terms of absolute value, like you would in geometry. Just get the area. And then after, if it's below the x-axis, treat it negative. If it's above the x-axis, treat it positive. The reason why I'm saying that is you don't want to get hung up with like this triangle over here. Technically, the x values are negative and the y values are negative. We're not really using the values. We're just saying anything below is negative. So calculate the area, and then if it's below, treat it negative. If it's above, treat it positive. So let's take this graph and evaluate some of the integrals. So notice the difference here are the intervals that they're taking us on. So our first one is the integral from -7 to -2. So that's our triangle here below the x-axis. So the base is 1, 2, 3, 4, 5, and then the height is 1. So the area on this interval, well, let's just do the work over here. Area is 1/2 base times height. Doesn't really matter the order we multiply, but I'm going to do 1 times 5 like that. So 1/2 of 5 is 2.5 in terms of absolute value. But when we define it as an integral, since it's below the x-axis, it's negative. below x-axis is negative. Integrals have assigned area. Then the next one is taking us from -2 to 2. Well, that's our semicircle piece. So the area of our semicircle is pi times this radius is 2 squared. And now I'm dividing by 2, not 4, because it's the whole half a circle. So 2 squared is 4 divided by 2. So I'm going to get 2 pi, and this is above the x-axis. Good. Next one is taking us from 2 to 4.5. From 2 to 4.5. So I've got this triangle here. Now, you could do this as 2 separate triangles if you wanted to, or you could just do one big triangle. I would do one big triangle. I've got 2.5 as the base, and then the height is the perpendicular distance. So it would be the distance down the center here of 3. So this is 1/2 base times height. So 2 times, well, half of 3 is 1.5 times 2.5. So without the use of a calculator, you might want to do that off to the side here. 5, 2, 12, 5, 2, 3, 7, 5, 2 decimal places. So we've got positive 3.75. And then our last one is that little mini triangle below the x-axis, so it's negative. So that base is just 1/2 itself. And then the height is 1. So 1/2 times 1/2 is 1/4, or 0.25. But anything below the x-axis, we're going to make negative. Last problem brings us through the whole interval from -7 all the way up to 5. So this is going to be the cumulative area. Everything above the x-axis is positive, below the x-axis is negative. So I'm just going to go left to right. I had a -2.5, then a positive 2 pi, then a positive 3.75, and then a negative 0.25. If I had to combine like terms, 3.75 minus 0.25, that's 3.5, just thinking in terms of like money. 375 minus 25 cents is 3.50. Then minus 2.50, we're left with $1 plus 2 pi. As the cumulative area under the curve, where anything below the x-axis is negative, above the x-axis is positive. Questions? All right. The last part of this is going to kind of force us to review again our notation for integral, but also just then finding the value instead of just rewriting it. So our last part says translating notation and finding definite integral values. The graph above consists of a quarter circle, a half circle, and 4 line segments. This is what I mean, that they have to tell you that so that you know that you're using your circle formulas and your that those are straight lines. For each of the expressions below, fill in the missing limit of Riemann sums, then determine the value of each integral using geometry formulas. All right, so first we're going to practice getting the limit of the Riemann sum. All right, so if this definite integral from 12 to 16 I'm just going to mark it here so we kind of know what we're looking for. The easy part's going to be getting the area. The hard part is writing it as a Riemann sum. So let's start with our delta x, b minus a, divided by n. So that's 4 over n. And then what do we need? We need our x sub k. All right, so my x sub k is a plus delta xk. And then I look at the function and I realize I kind of didn't need that because it's a constant function. There's no x to plug in. So I did it just to kind of keep things consistent, but I really don't even need this. I've got the limit as n goes to infinity of the summation from the first to the last. The height is a constant -2, and the base is 4 over n. So that's our limit of the Riemann sum. The value of the integral is as easy as base times height. 1, 2, 3, 4. Height of 2, but it's below the x-axis, so negative. Just put a negative in front of there, -8. All right, next one is from 3 to 9. All right, this is actually our most difficult one here, from 3 to 9. Remember that the area dx with respect to the x-axis is actually the area underneath the semicircle. Not as nice as just filling in the semicircle. It's got to be with respect to x. First, let's do our Riemann sum. My delta x is b minus a divided by n. So that's 6 over n. And my x sub k is a, which is my 3, plus delta xk. So the limit as n goes to infinity, whoops, sorry about that, always stays the same, of the summation from 1 to n. And now this one's going to be a little tricky to plug in. It's going to be a little bit long here. So I've got 4 minus square root of 9 minus, and then in parentheses here, instead of the x, I got to squeeze the 3 plus 6 over nk, and then finish out that that's minus 6 squared. And then my dx, I can't really fit it, is the 6 over n. That's a 6 over n at the end here. Maybe I should move it down because it's like right over that integral. Let's try. Erase. So this is squared, and then I'll just put down here times 6 over n. So we could see it. The area is actually a little bit tricky too. Who has a plan? How do I get the area below the semicircle?
Can you get the area of the semicircle and then, well,
Yes.
and then minus?
From what?
From the area below? Wait, but then you'd already found the area below.
We're gonna find
Oh, you get the area of the square, the rectangle, and then minus the area of the semicircle.
Perfect. So when we do the semicircle is pi times, well, the radius here, we got to find the middle. So the radius is 1, 2, 3. So 3 squared, and it's half of it. So we've got 9 pi over 2. And then the whole rectangle here has a base of 1, 2, 3, 4, 5, 6, and a height of 1, 2, 3, 4. So the area is 6 times 4, which is 24 of that rectangle. This is all above the x-axis, so positive. So we've got 24 minus 9 pi over 2 as the area below the semicircle, but above the x-axis. Good. The next one here, let me move up. There we go. From 0 to 3. So from 0 to 3, let's get a different color here. That like orange color. There we go. I like it. 0 to 3, I see a trapezoid. Fine if you see a rectangle and a triangle, but I'm pushing trapezoid on you to get you ready for tomorrow. All right. Delta x, let's do our Riemann sum. B minus A divided by n. So 3 over n. And our xk is 0 plus 3 over nk. When I plug it in, I'm not going to write the 0 in there. So limit as n goes to infinity. Summation k equals 1 to n. Then we've got our 2/3, and instead of an x, 3n times k. And then that's plus 2. And dx is our delta x again. Area formula for a trapezoid. I've got 2 parallel vertical bases of 2 and 4. And that makes the height the 3 boxes. The height is the perpendicular distance between those 2 bases. So height over 2, parallel bases 2 and 4. So 3 halves times 6 is 9. Questions? All right, almost done. -2 to 0. So that's this quarter of a circle. Let's first get our delta x. B minus A over n minus a negative is going to make a positive 2. X sub k, -2 plus 2 over n times k. So now I can build my limit as n goes to infinity. Summation from the first to the last rectangle. Now I'm going to look at f of x, square root of 4 minus x squared, square root of 4 minus, and instead of the x, my -2 plus 2 over nk squeezes itself in that spot. And then the dx is my 2 over n outside of the radical, though. Make sure delta x isn't underneath the radical. And this one is above the x-axis. It doesn't matter that it's to the left of the y-axis. Above the x-axis is what's determining the sign. And pi times the radius this time now is just 2 squared, but it's only quarter of a circle. So we divide by 4. That's not a whole semicircle. So this is just going to cancel to be pi. Anything above the x-axis is positive. Then they're making us look at the interval from 9 to 12. 9 to 12. Notice that it's okay that there's a like a hole in the graph there and a jump discontinuity. As long as we're not being asked to kind of jump over that, we can take the area right up to it. The delta x is b minus a over n. So 3 over n. And this time I'm not even going to write my x sub k because I'm noticing it's a constant. I don't need to plug in an x. So my limit as n goes to infinity from the first to the last rectangle is a height of 4 and a base of 3 over n. And the height of 4 and the base of 3 is what we have to multiply to get our area above the x-axis, so it's positive. All right, last but not least, we've got our integral from 16, where's 16? Here we go, to 22. Oh, okay, this is a little bit below, a little bit above. We're gonna have triangle below, and then a triangle above. So when we do area, it's going to be a net area between the two. Let's first get our Riemann sum, delta x, 22 minus 16, divided by n, 22 minus 16, 6 over n. xk, 16 plus 6k over n. The limit as n approaches infinity of the summation from our first to our nth rectangle. Take our function, 2/3 times, but now instead of an x, we've got to plug in there the 16 plus 6k over n minus 19. Now I need another parenthesis in here to close in my x minus 19, and then my dx at the end of this. Gosh, these look so horrible, the limit as the Riemann sums. Once you understand them, it's not that they're so complicated to write, but they look very, very complicated. A lot of parentheses. All right, so area below the x-axis. The base is 3 and the height is 2. So 1/2 of 3 times 2 is 3. Half of 6 is 3. And then look at the space above. Oh, it's exactly matching. 3 times 2. Half of 3 times 2. We get a positive 3 up there. So when we're calculating the area, it's the net area. A negative 3 plus the positive 3 is actually going to cancel out and be a 0 cumulative area. The area below is equal to the area above. So whenever you have equal areas below and above the x-axis, it's going to become a net area of 0. And seeing things like that when we get back into our full physics application lesson is going to kind of help us understand displacement. If you haven't moved, you wind up at the same location, things like that. Questions? All right, homework again is Delta Math tonight. I'm here 10 period if anyone wants to do the homework or has any questions.